ever known, and it is dying. But before it goes completely silent forever, it sent back something, data, readings, signals from a place no human eyes have ever seen, and no spacecraft had ever reached before. And what it found out there in the cold dark between the stars has quietly shaken the foundations of everything scientists thought they knew about the universe we live in. Something is wrong with the picture we have been given of our solar system. Not slightly wrong, not off by a small margin. Fundamentally, structurally wrong in ways that most science broadcasts refuse to sit with long enough to explain properly. And the machine that revealed this uncomfortable truth was not some billion-dollar modern marvel launched in the age of supercomputers and artificial intelligence. It was a spacecraft assembled in the 1970s, running on technology less powerful than the phone currently sitting in your pocket, carrying instruments that were designed before the internet existed, before personal computers existed, before most of the people reading this script were even born. That machine is Voyager 2, and what it has been sending back from the edge of everything, and what it found when it got there, is one of the most quietly staggering stories in the entire history of human exploration. Think about what it means to truly leave the solar system. Not in the poetic sense, not the metaphorical sense, but physically, measurably, in the hard language of instruments and data. For billions of years, our sun has been exhaling, the constant exhalation, a torrent of charged particles. Called the solar wind, pushes outward in every direction, forming an enormous invisible bubble around all the planets, all the moons, all the asteroids and comets that orbit our star. Scientists call this bubble the heliosphere, and for most of human history, it existed only in theory. Nobody had ever measured it from the inside. Nobody had ever crossed it and looked back. Nobody had ever been outside it to tell us what was on the other side. Until Voyager 2 crossed that boundary on November 5th, 2018, at a distance of approximately 119.7 astronomical units from the Sun, which, in numbers you can hold on to, is roughly 11 billion miles from Earth. And the moment it crossed that invisible threshold, it entered a realm that no instrument built by human hands had ever directly sampled before: the interstellar medium, the space between the stars. But here's where it gets interesting, because what Voyager 2 found at that boundary was not what anyone predicted. Researchers discovered that the interstellar magnetic field is approximately 2 to 3 times stronger than prior models had estimated. And this means, in turn, that interstellar particles exert up to 10 times as much pressure on our heliosphere as scientists had previously calculated. Read that again. 10 times the pressure. The bubble of protection that our sun creates around the entire solar system, the same bubble that shields Earth from a constant bombardment of galactic cosmic radiation, the same invisible armor that makes complex life possible on this planet, is being squeezed from the outside with a force that our best theoretical models had dramatically underestimated. For decades, scientists had run their equations with the wrong numbers, and it took a machine the size of a small car, traveling at 34,000 miles per hour through the void between stars, to correct them. This is not a minor calibration issue. This is a structural revelation about the nature of our cosmic neighborhood, and the implications run deeper than any headline has properly captured. The plasma inside the heliosphere runs hot and sparse, while the plasma in interstellar space is colder and denser. The space between stars is also filled with cosmic rays, particles accelerated by the violent deaths of exploding stars elsewhere in the galaxy. Voyager 1 had already established that the heliosphere blocks more than 70% of that radiation from reaching us. 70%. Without that invisible magnetic shield, the radiation environment on Earth would be catastrophically different. Life as it exists here might not exist at all. But we only confirmed this because a 720-kilogram spacecraft built nearly 5 decades ago happened to survive long enough and travel far enough to measure it directly. That is the thread by which this knowledge hangs. And it gets more complicated still, because even the shape of the heliosphere, the very geometry of our protective bubble, turned out to be wrong in ways that challenged fundamental assumptions. Research published in early 2024 suggests the heliopause may be shaped differently than once believed. Instead of a thin boundary line between solar space and interstellar space, new evidence points toward a thick boundary layer. The transition zone that Voyager 2 crossed was not a clean line. It was a murky, compressed, complicated region where solar wind and interstellar wind push against each other in ways that are still being mapped, still being debated, still being revised. Scientists observed that the plasma is compressed around the inside edge of the heliosphere's bubble, and they still do not fully understand what is causing this compression on either side. If the heliosphere is likened to a ship sailing through interstellar space, it appears the hull is somewhat leaky. Our protective bubble leaks. The shield we have taken for granted, the invisible armor that has made the evolution of life on Earth possible, has gaps in it that we are only now beginning to understand. And we are only beginning to understand them because of one aging spacecraft running out of power at the edge of everything we know. But here is the layer that most coverage never reaches, because the story does not end at the boundary. It continues into what lies beyond. Both Voyager 1 and Voyager 2 detected a searing hot region of space at the edge of the heliosphere where temperatures spiked to an estimated 30,000 to 50,000 Kelvin. That is a wall of heat sitting at the outermost edge of our solar system's influence, a temperature so extreme it defies the intuitive expectation of what you might find at the cold, dark fringe of interstellar space. Nobody had predicted it at that magnitude. Nobody had modeled it. It was simply there, measured, undeniable and unexplained. A blazing threshold between the world we know and the universe beyond it, sitting at temperatures that make the surface of some stars seem cool by comparison. And when both spacecraft independently confirmed it from different positions, from different directions in interstellar space, the scientific community had to confront the fact that the edge of our solar system is a far stranger, far more violent place than any textbook had ever suggested. Think about what that means for every model we have built about how the solar system interacts with the galaxy around it. Think about every assumption baked into our understanding of how cosmic radiation travels, how magnetic fields behave at boundaries, how the interstellar medium shapes the environments of planetary systems across the Milky Way. All of those models needed revision, and the revision only became possible because Voyager 2 was there. Recent data from the Voyager spacecraft's plasma wave instruments have revealed increasing electron densities as the probes move deeper into the interstellar medium. Voyager 1 has detected a broad density peak, with electron densities remaining relatively constant at about 0.147 electrons per cubic centimeter beyond 160 astronomical units, suggesting it may have entered a new regime of the interstellar medium. Voyager 2 continues to observe electron plasma oscillations, indicating ongoing interactions with shocks and pressure fronts in the very local interstellar medium. These are not just numbers. These are the first direct portrait humanity has ever drawn of the environment that surrounds our entire solar system. Every other star we study, we observe from the outside. Every other planetary system is a dot of light measured across impossible distances. But our own neighborhood, the actual texture and density and electromagnetic character of the space our sun moves through, we are mapping for the first time in real time through instruments on a spacecraft launched by engineers who used slide rules. And this is where everything changes. Because now those instruments are going dark. One by one, in a carefully planned sequence, NASA has been powering down the eyes and ears of Voyager 2. Not because the mission has failed, not because the science is done, but because the spacecraft is dying in the most literal, unavoidable sense. Voyager 2's radioisotope thermoelectric generators, which convert the heat from decaying plutonium into electricity, collectively supplied 470 watts at launch, losing power continuously over the decades. All 5 instruments had been expected to continue operation through 2026, but the pace of shutdowns has accelerated as the power budget has tightened further than projected. Each year, each instrument that powers down takes with it an irreplaceable window into a region of space that no successor mission is yet designed to reach. By late 2024, 6 of the spacecraft's original 10 instruments had already been deactivated. The plasma science instrument, which measured the number, speed, and direction of electrically charged atoms flowing past the spacecraft, was shut down on September 26, 2024, because it had become unavoidable. The plasma instrument, the one measuring the actual charged particle environment of interstellar space, gone. Then, on March 24, 2025, the low-energy charged particle instrument was shut off, leaving Voyager 2 with just 3 functioning science instruments. 3 instruments on a spacecraft 13 billion miles away, each one consuming a fraction of a watt of power from a slowly dimming nuclear source, each one irreplaceable in what it sees. What most people are not seeing in this story is the true weight of what these shutdowns represent. This is not like turning off an old laptop. This is humanity closing its eyes to a region of the universe it cannot otherwise observe. There is no other spacecraft near the heliopause. There is no backup. There is no instrument we can send in Voyager 2's place that would arrive in any of our lifetimes. The New Horizons spacecraft, famous for its flyby of Pluto, is heading in that direction, but it will not reach the heliopause for another 2 to 3 decades, and it carries fewer instruments with less capacity to measure what Voyager 2 has been measuring. What Voyager 2 knows, what it has been whispering back across 13 billion miles of vacuum, is knowledge that exists nowhere else. And every instrument shutdown is a sentence in that transmission that will never be completed. NASA's Voyager project scientist at JPL, Linda Spilker, put it plainly, every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be our last. But that day could also bring another interstellar revelation. Every day could be the last. That is not a dramatic flourish. That is the honest operating reality of a mission now approaching its 5th decade. running on a power source that was expected to give out years ago, surviving through a combination of engineering ingenuity, careful power management, and, it must be said, a measure of luck that defies reasonable expectation. Because the survival of Voyager 2 at this point is itself a scientific miracle. The spacecraft has endured radiation environments that should have degraded its electronics beyond function. It has navigated through temperature swings that would destroy most modern components. Its thrusters have been fired and refired across decades without failure. Its antenna has remained precisely pointed at a planet so far away that the light from the sun, traveling at 186,000 miles per second, takes more than 17 hours to reach it. NASA engineers have described Voyager 2 as the longest letter humanity has ever written, and now we are reading the last lines. And those last lines are still carrying meaning that we are only beginning to decode. Consider the timeline in full, because it is more breathtaking than any fictional narrative could manufacture. In 1977, the engineers who assembled Voyager 2 designed it for a primary mission of 4 years. It was meant to visit Jupiter and Saturn, snap some photographs, collect some data, and fall silent. Instead, a rare alignment of the outer planets, an alignment that occurs only once every 175 years, allowed NASA engineers to thread an audacious trajectory that sent the spacecraft swinging past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. Voyager 2 remains the only spacecraft in history to have visited all 4 of the solar system's giant planets. 4 planetary systems, each one a revelation, each one a complete scientific story in its own right. At Jupiter, Voyager 1 and Voyager 2 together discovered new moons and revealed Jupiter's ring system, which had been hidden from view. At Saturn, they returned images of the ring system in extraordinary detail, revealing structures within the rings that no telescope from Earth could have resolved. At Uranus, Voyager 2 became the first spacecraft in history to observe the planet at close range, discovering 10 previously unknown moons and revealing an atmosphere unlike anything else in the solar system. At Neptune, Voyager 2 captured its final photographic images, a haunting view of Neptune and its moon Triton from a distance of more than 4.7 billion kilometers from Earth, before its cameras were permanently switched off to conserve the spacecraft's dwindling power. That image of Neptune and Triton hanging side by side in the black, taken in August 1989, marked the last time Voyager 2's optical systems were used. The cameras went dark, but everything else kept going. And then it kept going for 35 more years. 35 years of continued operation after the primary mission ended. 35 years of data, 35 years of a machine refusing to die, traveling outward, measuring everything it could still measure, sending signals back across distances that grow by approximately 35,000 kilometers every single hour. On June 28, 2025, NASA's Deep Space Network received a weak signal from Voyager 2 after weeks of radio silence. The spacecraft had been eerily quiet, a disturbing development for a mission already years past its original lifespan. Weeks of silence. No signal. For the engineers at JPL who have dedicated careers, in some cases entire working lives, to this mission, those weeks of silence carry a specific dread that is difficult to fully articulate. Because every engineer on the Voyager team knows that one day the silence will not end. One day the signal will stop coming, and it will not be a glitch. It will be the end. And the challenge, the gut-wrenching challenge, is that from 13 billion miles away, it is sometimes impossible to know in real time which silence is which. The signal came back, but each episode of silence, each anomaly, each unexpected behavior from a spacecraft so far away that a command takes 17 hours to arrive, and a response takes another 17 hours to return, is a reminder that the clock is running down. When something goes wrong with Voyager 2, and at this age, in this environment, things do go wrong, the team at JPL cannot simply push a button and fix it. They send a command, wait 17 hours, see what happens, and respond. A 34-hour feedback loop. Every troubleshooting session is a 2-day exercise in patience, expertise, and the ability to solve problems with technology that has not been manufactured or supported for decades. Of the 10 science instruments each Voyager spacecraft originally carried, 7 have been shut off so far. The team shut off the low-energy charged particles instrument on Voyager 2 in March 2025. On April 17, 2026, NASA shut down Voyager 1's low-energy charged particle instrument, an instrument that had been operating almost without interruption since Voyager 1's launch in 1977 for nearly 49 years. Nearly half a century of continuous operation from a single instrument, finally falling silent. The shutdown command took 23 hours to reach the spacecraft. The shutdown process itself took 3 hours and 15 minutes. And somewhere in that sequence, in those 26 hours of transmission and mechanical response, one of the longest-running scientific instruments in history took its final measurement. With the implementation of the current power conservation plan Engineers believe the two probes could have enough electricity to continue operating with at least one science instrument into the 2030s. But they are also mindful that the Voyagers have been weathering deep space for 47 years, and that unforeseen challenges could shorten that timeline into the 2030s. That is the hope. That is the plan. But plans built on plutonium decay curves and 47-year-old electronics have a way of meeting reality on their own terms. What the world has not fully absorbed is what the end of the Voyager mission will actually mean. It will not simply be the loss of a spacecraft. It will be the loss of a vantage point. Think about what that means. The data Voyager 2 is sending back today, right now, at this moment, is data from a place that will not have a replacement observer until the late 21st century at the earliest. The scientists who would build that future mission have not all been born yet. The engineers who would operate it are children today, if they exist at all. What Voyager 2 is doing in its slow, dimming, instrument-by-instrument withdrawal from the cosmos is closing a window that will not open again for generations. The unexpected measurements of magnetic field strength and plasma density that the Voyagers have been collecting suggest they are exploring a genuinely unknown region of space. The definition of the boundary the craft passed is still being written. Still being written. Not finalized, not understood. Still, in 2026, after decades of data collection, the most basic questions about where exactly our solar system ends and interstellar space begins are questions that science is still actively working to answer. And the only instruments that can answer them in real time are slowly going dark, one by one, at the edge of the known universe. Current measurements indicate that the interstellar density has increased further from the value it had outside the heliopause, but no one knows what will happen next. No one knows. That phrase, simple, honest, and somehow shocking when attached to a mission nearly half a century old and billions of dollars in the making, is the most scientifically important thing anyone has said about Voyager 2 in years. The numbers are changing. The interstellar environment is not static. It is dynamic in ways that challenge assumptions, that demand explanations that current models cannot yet provide. And the spacecraft that is watching it change, that is the only thing capable of watching it change from this particular position in the cosmos, is losing power at approximately 4 watts per year. 4 watts per year. The energy of a dying nightlight, lost annually from the only human instrument operating at the frontier of interstellar space. The project manager at NASA's Jet Propulsion Laboratory, Dr. Suzanne Dodd, described this moment as not just a technical milestone, but a deeply human one. We're watching the slow farewell of a spacecraft that has taught us more about our place in the universe than almost anything else. A slow farewell, not a dramatic explosion, not a catastrophic failure, just a gradual dimming, a quieting. Instrument by instrument, watt by watt, the most well-traveled machine humanity has ever built is falling silent in the dark between the stars. And there is a particular grief in that. Not the sharp grief of sudden loss, but the long, measured grief of watching something irreplaceable fade away while you still have the ability to hear it. The legacy, though, is already permanent. What Voyager 2 discovered at Jupiter rewrote the textbook understanding of that planet's moons and ring system. What it found at Saturn gave planetary scientists data they are still publishing research about today. What it revealed at Uranus and Neptune, 2 planets no other spacecraft has ever visited, remains the only close-range observation humanity has ever made of those worlds. And what it has been measuring in interstellar space from the moment it crossed the heliopause in 2018 to the present day has altered our understanding of the environment our solar system moves through, the nature of the boundary that protects us, and the true character of the galaxy we inhabit. As of January 2026, both Voyager spacecraft are more than 13 billion miles away from Earth, continuing to operate and communicate from interstellar space in what NASA describes as survival mode. Still alive, still transmitting, still returning data from the frontier of human knowledge. Survival mode. There is something profound in that language. Not thriving, not at peak performance. Surviving. Sending back what it can, with what it has left, from a distance so vast that the signal arriving at Earth's receiving stations is weaker than the power of a single snowflake landing on the ground. And yet it is still there, still transmitting. Still, after nearly 5 decades and 13 billion miles, and the death of every non-essential system on board, doing what it was built to do. But the questions it has raised, the questions it has opened without answering, the doors it has cracked without fully unlocking, those will outlast the mission by decades, perhaps centuries. What exactly is the structure of the heliosphere's boundary, and why does it not match any model we have built? What is creating the blazing wall of heat at the edge of the solar system, and what does it mean for the habitability of the space around our star? Why is the interstellar magnetic field so much stronger than predicted? And what does that say about the forces shaping planetary systems across the galaxy? Why is the interstellar plasma density still rising as Voyager moves deeper, and what will it look like at distances no probe has yet reached? These are not abstract academic questions. They are questions about the fundamental environment of the solar system that produced life on Earth. They are questions about the shield that protects us, and about what exists beyond it, and about how stable and how permanent that protection really is. And they are questions that, for now, have only one instrument capable of contributing new answers. An instrument running on the fading heat of decaying plutonium, drifting alone through the darkness between the stars, billions of miles from any human hand that could ever reach it. When Voyager 2 finally goes silent, and it will go silent, whether this year or next year or sometime in the decade ahead, there will be no memorial, no ceremony in space. The spacecraft will simply continue its trajectory, continuing to drift outward at 34,000 miles per hour through the interstellar medium long after the last signal has faded. In about 296,000 years, it will make its closest approach to the star Ross 248 in the constellation Andromeda. In tens of millions of years, it will continue drifting through the Milky Way, carrying on its antenna a gold-plated record containing the sounds and images of Earth, a message in a bottle thrown into an ocean so vast that no reply could arrive for millions of years. But here, now, in 2026, what remains is the question that the data keeps asking without answering. What is really out there in the space between the stars? What else exists in the interstellar medium that no model has predicted, that no theory has prepared us for, that only a direct measurement from inside that region could reveal? And the deeper, harder question underneath all of it, the one that Voyager 2's instruments, even now, are perhaps collecting the last data points to address. Is our solar system's protective bubble genuinely stable and genuinely sufficient? Or is it stranger, more vulnerable, and more dynamic than we have ever allowed ourselves to believe?